Plant frequency, an overview. Frequency measures reflect the likelihood of encountering a plant species at any location in an area of interest. Frequency is defined as the number of times a plant species is present in a given number of uniformly sized quadrats that are placed repeatedly across a stand of vegetation. Frequency measurements focus on the presence of species within the quadrats. So this is an important distinction from density. Frequency measurements are very sensitive to changes in the size of the quadrat, so that's why it's part of the definition. And so two aspects that we must always remember when we're dealing with frequency is that we're talking about presence or absence of species, and the size of the quadrat is an important characteristic of the method. We use frequency data to monitor changes in vegetation. It's very sensitive to changes in vegetation, and so we can use it to assess trends. We use it to compare one site through time, so we can collect frequency data in multiple years and look at how the vegetation has changed at one site, or we can use it to compare two different sites that have the same species. The calculations for frequency are fairly straightforward because it's the proportion of the number of plots in which a species occurs divided by the total number of plots that are examined. And we multiply this by 100 to calculate it as a percentage. Frequency is always reported as a percentage. So let's look at this graphical illustration showing three different plant species. There's a grass, a daisy, and a thistle. And there are three different quadrats that are located in this macro plot of vegetation. To calculate the frequency of thistle, we see first that the thistle occurs only once out of three quadrats, and so that's 33% frequency. The daisy is found in two of the three quadrats, so 67% frequency. And we find grass in each one of the quadrats, so that equates to 100% frequency, because 3 plots divided by 3 plots equals 100%. One thing I do want to point out is that the fact that there are 3 grass plants in this quadrat does not matter, because we're only looking for presence. So all you need is one plant in order to record the presence, and the number of individuals in the quadrat is not recorded. It does not affect the frequency measurement. Frequency is related to density. So here we're going to look at an example where we have two different species, a dandelion and a daisy, and again we're measuring frequency using only 3 quadrats. In this case, we're going to measure density, and we can see that we have 4 plants of the dandelion in these 2 quadrats. We also have 4 individuals of the daisy in this quadrat. So both of these species have the same density, 1.3 plants per plot, but their frequency is different. The dandelion occurs in 2 out of 3 of the quadrats for a frequency of 67%, while the daisy is found only in 1 of 3 quadrats for 33% density. 33% frequency. Frequency is also related to the spatial distribution of vegetation. So here we see 2 examples. You can think of them as macro plots of tree species, and we've got 9 plots in each one of these, and these have the same number of individuals, so the density of the macro plot is the same, but what's different is on the left we have a clumped or patchy distribution of vegetation, and on the right it's more homogeneously or evenly distributed. The species occurs in only 3 of 9 quadrats or plots in the vegetation on the right or on the left, and so that equates to a frequency of 33%, whereas in the more evenly distributed vegetation, 8 out of 9 quadrats contain the plant, and so that equates to a frequency of 89%. The only difference here that affected the frequency is the spatial distribution of the individuals. What are the advantages of frequency? First, it's objective and repeatable. The decision is simply presence, and so there's not much room for bias or subjectivity on deciding whether or not an individual is included in the plot. This also makes frequency very repeatable between observers. It's relatively rapid to measure because there's not a lot of time. You don't have to spend time determining how many individuals there are, simply whether or not they are in the plot. And this makes it relatively simple to do and requires relatively little training for observers. Frequency measurements are relatively stable to environmental fluctuations that we would expect to see during with seasons, changing seasons, or even between years. It's also relatively stable to biomass removal by grazing. So that's one of the advantages for it, because it does provide us with good information about vegetation change. There's no need to distinguish individuals, which saves a lot of time in examining the plots. And as I mentioned, it is a very sensitive indicator of real vegetation change. Frequency is affected by both density and plant dispersion, and so this is an advantage because when those characteristics change, we're able to detect it, but it's also a disadvantage. And you may ask why. Well, it's because it's sensitive to both density and spatial distribution of plants. We don't know when we see a change in frequency whether it's due to a change in density, a change in the spatial distribution, or both, unless we collect other information at the same time as the frequency data. It's sensitive to quadrat size. And because of that, if we're focusing on more than one species, we may need to use multiple sizes of quadrats in order to collect frequency data. We usually identify species to the plants to the species level, and so frequency requires excellent species identification skills. And frequency estimates can be sensitive to seedling numbers. If we have a large recruitment event or seedling emergence event, and we count a lot of seedlings, but if there's not good survivorship of those seedlings, we may artificially increase a frequency estimate compared to what would happen if we focused only on mature individuals. Frequency is also difficult to visualize. It's not an absolute attribute of plants. And what I mean by that is that density or, say, biomass of a plant can be measured. The density can be measured in a particular size quadrat or cover. Those are more absolute attributes. But because frequency is tied to the quadrat size, it's not actually something that is inherently a value of the vegetation. Okay, so what are the ground rules? First, we have to determine what counts as being either in or out of the plant. So what is our basis for including plants in our quadrats or plots? We also have to lay some ground rules or make decisions about the level of identification of plants as we do frequency measurements. There's always the question of how many samples are enough, so the sample size question is important for frequency measurements. And then, of course, the issue of selecting the appropriate quadrat size. Now, for all of these decisions, remember that they are driven by management objectives and often have to be made on a case-by-case basis. So let's examine the criteria for counting plants as in. As we see in this diagram here, this dandelion is rooted in the plot, as is this sod-forming grass. The dandelion here is not. And so our most common criteria that we use for frequency measurements is called rooted frequency. Now let's consider another situation. Shoot frequency is something that we may add as a criteria if we have species that produce stolons and can root in the plot. So if we had a larger grass that had stolons that occurred and the stolons were rooting down in the plant plot, or they have just having a stolon that does have meristematic tissue on it, that can be counted if we decide that we want to include shoot frequency. Canopy frequency is something that we include for larger plants, such as large shrubs and trees. And that's because the stem of the plant, or where the plant is rooted, may not occur in the plot. But the canopy certainly has influence over that area that's defined as the plot. And so we will define canopy frequency if any portion of the canopy of a plant occurs over the plot. And then the last case we call mere presence. And in this situation, what we're looking at are any presence of plant part in the quadrat or in the volume above the quadrat is considered as presence. So in this case, of course, we've got a rooted plant here, but having these leaves that are overhanging, that could be considered canopy, the stolons, or even some mat-forming plants that put out runners, we would consider present if we were using mere presence as a criteria for counting plants in the plots. Other decisions that we need to make have to do with the level of identification. The first is taxonomic level. I mentioned that we usually identify to the species level, but depending on what our management objectives are, or the species that we're working with, and the time of year at which we're measuring them, we may determine that it's really okay just to estimate to a genus level or even to a functional group level, although that's less commonly done. The age class is another thing that we need to consider. I mentioned earlier the problems that we can have with seedlings. Sometimes it makes it far easier for us to, in order to separate or isolate the influence of seedlings from more mature plants, is to actually record the frequency of seedlings separately from the frequency of saplings or mature individuals. And we can also look at this from a developmental stage perspective and look at whether they are seedlings, reproductive individuals, or senescent. And then we need to sometimes just say, well, we're not going to pay attention to the age class or the stage class as we collect frequency data. The last level of identification component that we need to consider is whether we want to count annuals. In some communities, annuals come and go so quickly that they can be a very ephemeral part of the community. And so we have to make a decision. Do we only want to focus on perennial plants? Do we want to count annual plants? And if we do count annual plants, how do we deal with plants that can be identified, but let's say that they have already gone through their life cycle and they're dead? So do we only count live annual plants, or do we count any plant that we can identify to the species level. Sample size is always a consideration. In general, in order to get good frequency estimations, we need to have at least 100 to 200 quadrats or plots in which we've estimated frequency. Now, it depends on our management objectives, of course, because if we need to detect small changes, we're going to have to increase the number of quadrats that we use in order to have greater sensitivity to vegetation change. Usually, for frequency measurements, the individual quadrats are arranged in a macro plot area, such as the one that you see here, and usually they're arranged systematically. In this case, we would consider each individual quadrat as an individual sampling unit. So we have independent quadrats, and we would analyze the data based on the total number of quadrats. Sometimes we arrange quadrats along transects, in which case we would then take an average frequency value for each species in the transect, and then the transect becomes the sampling unit. Let's look just for a minute at the importance of quadrat size. As I mentioned before, as we increase the size of the quadrat, the frequency is going to increase. We can see that with pink daisy, for example, on the left, we're using small quadrats and the frequency is 0. In the center, we're using larger quadrats, and the pink daisy is rooted in 2 out of 4 quadrats. And in the largest size quadrat here, it occurs in every single one for 100%. And this makes perfect sense, because frequency is going to increase if we use larger quadrat sizes, because the bigger the plot, the more area each plot is going to capture, and so it has a greater likelihood of capturing more plants. There are a few guidelines that we do use on how to determine what is the appropriate quadrat size. First of all, when we're doing frequency measurements and want to interpret the data, we have the greatest sensitivity when the frequency is between 20 to 80%. We like to target 30 to 70% for most species, especially for the species with which we have the greatest concern. And this is because of statistics and limitations of being able to detect changes at very, very low frequencies or at very, very high frequencies. Because of this, if the frequency is less than 10%, we need to increase our plot size. If frequency is greater than 90%, we need to decrease the plot size. It is far easier to collect frequency data if we only have one plot size, and so we want to try to use one size if that works for most species. But this is not always the case, and so we use nested plots if one size won't work for all species. A discussion of how to use nested plots and how to figure out what is the appropriate plot size is the subject of a subsequent lesson.